Let's go ahead and get started. Welcome back to ECE 320A. Homework 4 is due on Tuesday, and that's dealing with Chapter 12 material on Laplace transforms. How do you transform these? Either signals or signals that are you're performing operations on signals, and now you want to be able to combine these Laplace transform operations in a way that will allow you to find the Laplace transform of something a little bit more elaborate than what you see in maybe the Laplace transform tables. We will start, and we'll try to go over a few more of those to give you more information or more material to work from for Tuesday's homework assignment, or that's when it's due, and today we'll spend more time dealing with some of those ideas. And the first thing is to see how well you did on your homework assignment for today, or your class assignment for today, which is the first example in which the delay is different or is not going to be such that it's the same as the delay in the unit step or the switch, meaning your cosine waveform has now been delayed potentially a different amount than when you're switching it on, and so now the zero is not lining up with right when the cosine waveform kicks in at time 0. Then we'll look at some more operational transforms. Has everyone applied the ladder technique to circuit analysis? Do you know what I'm talking about? Have you ever heard it? So we'll deal with that when we get to that point in the lecture. It sounds like maybe that would be an interesting path to pursue. And now, well, we've talked about big top tents and poles, and now we need to talk about ladders so that we can get on that big top tent. We'll see if we can relate that to circuit problems. Then we will introduce the inverse Laplace transform and discuss what I have tried to classify as your two basic cases for performing inverse Laplace transform. You can boil everything, you can put all of your transforms into one of those two cases. That's the way I would like to proceed with inverse Laplace transforming. Let's then start by this example that we had mentioned last time. Suppose somebody wants to Laplace transform cosine 3t minus 5 u of t minus 1.5. And they want to call that then capital F of S. First thing you probably want to do is start working with the argument on your cosine waveform and see if you can relate that to the delay, because the delay in your unit step, you know exactly what that delay is. It's 1.5. You now want to see if you can rewrite the argument of your cosine waveform so that you can factor out explicitly that same amount of delay of t minus 1.5. The argument of the cosine waveform is 3t minus 5. And what we're wanting to do is factor out something when multiplied by 3 gives us 1.5, essentially. Because if we factor the 3 out, we want to find t minus 1.5 inside that argument. And 3 1.5 gives us 4.5. But we can't change, we can add 0 to anything we want, but we can't arbitrarily add a number or subtract a number. And right now we have actually altered the argument. We need to make up what needs to be remaining or added in, if the case may be. But in this case, we need to make minus 4.5 become minus 5, and to do that we can subtract an additional 1/2. And now we haven't changed that in any way other than to separate out some critical pieces. This now allows us to say, okay, now I can write 3t minus 1.5 minus 0.5. That is now how I want to express my argument, so that what I'm going to do in the cosine waveform is use this trig identity that hopefully you have in the back of your head. If not, remember Euler and you can derive it. And hopefully you'll always remember Euler. But here I'm going to just provide it. This is cosine A cosine B minus sine A sine B. And what I'm going to now be using is this is going to be my A, and this minus 0.5 is going to be my B. And that now allows me to say, okay, if I have this expression that I'm trying to Laplace transform, I now want to Laplace transform cosine of 3t minus 1.5 minus, 0.5, and I'm scaling that, or I'm switching it on at 1/2. Or I can now rewrite this and say, okay, that's equal to this Laplace transform of the cosine of 3t minus 1.5 cosine of minus 0.5, and this now gets scaled by u of t 1.5. Now I'm applying my trigonometric identity. There's cosine A, cosine B. And I now need to introduce my sine piece, or minus sine of 3t minus 1.5 sine of minus 0.5 u of t minus 1.5. And now I've simply rewritten the original expression as the sum of two sinusoids. And those two sinusoids are at the same frequency, 3 radians per second. Questions on where that came from? And I was able to do that by explicitly working with the argument of my original cosine waveform. Now all we have to do really is remember our transforms for cosine and sine. What's the cosine transform? If I said, what's the Laplace transform of cosine omega t, what is that one? What's downstairs? How could you get half of this transform correct, whether that was sine or cosine? That's going to be s squared plus omega squared, because you know that the roots of that should be complex. They should be on the imaginary axis. You should end up with roots at plus and minus j omega if you have a sinusoid, cosine or sine. And that's what you're looking for there in the transform. The cosine actually ends up with the s on top. Remembering that, we now can write down what f of s is. And the thing to note is, what do these terms that I've now highlighted in blue or underlined in blue, how do we transform those? Those are just constants. There's no function of the independent variable t. Cosine of minus 1/2 or sine of minus 1/2 will simply be a number. We now are scaling the cosine and sine piece. by a different number. And if you were playing along, you heard that scaling right there. Sorry. In this case, we have cosine of minus 0.5 times the Laplace transform of that delayed cosine, but we can incorporate that delay by that factor scaling, which is the complex exponential scaling. This becomes s over s squared plus omega squared. Omega is actually 3, and then we are delaying by that 1.5. And if we then take the sign of a minus, that's the minus the sign, so I'll incorporate those two negative signs and say now I have plus sine of 0.5. And what is the Laplace transform of the sine? I'll get the denominator. And the term that is introduced because of the time delay. What's upstairs? Omega, which in this case is 3. And that's now our Laplace transform. Question? Yeah, I sort of did a couple of things at once. Here I have the sine of minus x, sine of minus 1/2. I said sine of minus x was minus sine of x. And down below I simply said sine of 1/2 and not sine of minus 1/2. That negative comes and cancels that other negative to give me the plus sign in between the two terms in my Laplace transform. So the question was about that particular sign, and I believe that sign, S-I-G-N, is correct. Does that answer your question? What's cosine of minus 1/2? And I could have done the same thing there. That's cosine of 1/2. The only thing that's going to get you into trouble here is on your calculator, you need to make sure, am I working with arguments of radians or degrees? Question? Oh, you were going to answer? Oh, you were just stretching. Okay, sorry, we all need to stretch. That felt pretty good, actually. What's cosine of 1/2? We need to make sure that we realize that that's a radian value for the angle. And if your calculator is set in the mode of degrees, you need to convert that to an angle in degrees. Question?
So because this is all fundamentally an integral working in the Laplace transform, we can't just take that linear expression cosine. We can't just bring that through like a combination of functions. It has to be separated out like we did here in order to be valid.
I'm not quite sure I'm understanding the question, but we have to make sure if we start with this particular expression, which is where we started, we had a 3t minus 5 and a u of t minus 1/2. We need to factor out this t minus 1/2 in the argument of cosine and then figure out what we can do with what's left over. And what we're seeing is that, oh, this is just a delayed cosine with a phase shift. So now when you're sort of turning on the switch, you actually have a phase shift introduced, and you're not right at the beginning of your cosine waveform when you turn on the switch. And that 1/2 in radians then determines where you are, and since you're not there exactly at 0, you're going to combine sines and cosines to create that adjustment. Did anyone calculate this? What is the cosine? So if you did this and you were in degree, you would need to take the sine or cosine of that particular value. We have 90 degrees divided by pi, so we're talking about almost a 30-degree angle, not quite, that we're finding the sine and the cosine, and that gives us a feel for how large these are. This is just a number. This will be some number. Cosine of 30 degrees, roughly, is 0.8776. There's your scaling for that. And this particular piece then is almost a half, or 0.4794. Meaning you just have 90% of the first piece, which is the cosine piece, and 50% of the sine piece, and they're scaled also by this complex exponential. Is that making sense? Questions on that? Did everyone get that when they were working on it at home? The correct movement is up and down with your head, okay, on that one. And I have a camera here that I'm taking pictures and monitoring, so I can see which way the heads are moving, up and down or left and right, and then that will get captured in the grade book. We're working on some of those as senior projects, capstone projects. How to take biometrics from the classroom. Let's now talk about Laplace transform operations, or operational transform, or Laplace transform theorems. Here I'm going to say number 2. We just talked about the shifting theorem where we shift the time. Now let's actually worry about shifting the frequency variable. So I'll call this the complex frequency variable, or just think S. That's S. And what we want to do is translate that. Or this operation pair says that if we translated the complex frequency variable S by some value A, so now we've shifted the complex frequency variable by A, or everywhere we had an S in our transform before, we replace it with S plus A. In the time domain, what that really means is that whatever we had for f of t, now we've introduced an exponential decay on that f of t. That's the transform theorem, the complex frequency variable translation theorem. And I'm sure you're all wondering why. That's what you ask, right? If you now look at the definition of the Laplace transform, we are looking at e to the minus at f of t. That's now our new function that we are wanting to Laplace transform. That you could say is a g of t. We weight that by e to the minus st, and we integrate out the time variable. But this can be made to look like what we're used to seeing if we simply combine our exponents. We could say, oh, f of t, but now we have e to the minus s plus a t dt. And that should look very familiar to you. It's just the Laplace transform, standard Laplace transform, except now instead of s, we have s plus a. So in the frequency domain, translating our complex frequency variable s by an amount a means that you're actually in the time domain hitting your waveform with a decaying exponential. Here's an example of that. You already know how to transform cosine. That's this s over s squared plus omega squared. What if somebody says, oh, well, that's not that interesting. Why don't we do a exponentially damped cosine waveform, where the damping rate is e to the minus 4t, and you should start to feel comfortable thinking about what that looks like as a function of time, that expression. You have the cosine of 3t, and now you're squishing it with this exponential decay. What's that transform into? What's downstairs? When you have a cosine or a sine, you look at its frequency, and now you say, oh, downstairs I have s squared plus 3 squared. But what did we just learn? We need to replace the s with s plus a. What's a in this case? It's 4. And we had an s upstairs in the normal undamped cosine waveform. Now we replace that s with s plus 4. And that's now the Laplace transform of an exponentially damped cosine waveform. Meaning we are going to use this theorem a lot. We'll have a lot of exponentially damped sines and cosines. Now, what does that mean if somebody said, where are the poles of that? I know you're all wanting to go to the circus again, but now where are the poles of this transform? This is written in such a way that you can explicitly see where the complex poles are located. What if this 4 was not there, where would your poles of the denominator be? Or the roots of the denominator, which are the poles of the transfer function. Where are the roots of the denominator if that 4 was a 0? S squared plus 3 squared says you've got poles at plus and minus j3. Now what that 4 is saying, what value of s causes the denominator to vanish? If you plugged in s equal to minus 4 plus j3, or minus 4 minus j3, that's going to cause that denominator to vanish. What we've done then is we've moved off of the imaginary axis over an amount a into the left half plane. This is an exponentially damped cosine. It's decreasing in time. I'm sort of hinting at what we will be becoming more familiar with later. But this would be and that corresponds to this s over s squared plus omega squared. The other poles, these guys now give us poles at minus 4 plus and minus j3. So now if we had, and this 4, this minus 4, is the minus a that we had up above. And we're always moving, if it's a negative value, we're moving into the left half plane. As a function of time, we had this, that's a terrible decaying exponential, but this is supposed to be e to the minus 4t cosine of 3t. And you may want to sketch that out for yourself to make yourself feel more comfortable with how that decay influences how quickly you damp that waveform out. If you move that blue X further into the left half plane and become more and more negative, what's going to happen to your time domain waveform? This number is going to, just the 4 would get bigger. It would be e to the minus 10t, e to the minus 20t, and this is now going to collapse much more rapidly. The oscillation frequency we haven't changed. If we simply go translating horizontally to increase that value. Questions on that? That's the complex frequency variable translation theorem. Let's now look at one more theorem called the scaling theorem. Now let's deal with A positive and say that we scale the time axis. And whether A is less than 1 or greater than 1 influences whether you're expanding or collapsing that time axis. But let's just concentrate on positive A's for now. And this now says, oh, if I scale the time axis, my transform will actually get, not only will I change the frequency variable, I'll scale the frequency variable, but I will also scale the entire transform by 1 over A. What age are you when you always say y, 2, 3, what? All ages if you're an engineer, but here, y, well, let's see. This is now from 0 to infinity, f of at, e to the minus st dt. That's by definition of the transform of f of at. We could maybe make this look more like what we're comfortable with by simply changing the variable and just say, well, let me make tau my variable of integration. And now I have d tau is a, whoops, dt. Or if I need to write t, which I will in a minute, that's tau over a. And dt then becomes this 1 over a d tau. Or this integral now is going to be, and what am I integrating with respect to? What are my limits? Tau now started with t equal to 0 minus. Tau is also 0 minus. If t is infinity, tau is also infinity. And now I have f of tau, e to the minus s. T now is tau over a, and dt is 1 over a d tau. And this now, if you pull things together properly, you're now integrating with respect to tau. You have f of tau, e to the minus s over a tau d tau, and that looks just like we claimed it would. And the thing to keep in mind here on this particular transform is to recall, or let me say remember, how t and s are related. They're reciprocally related, aren't they? They're reciprocals of each other. If you look at this e to the minus st, you want that exponent to be dimensionless. T, you know the units of. That's seconds. So s must have units 1 over second. So it's a frequency variable. That's why we call it the complex frequency domain, or the S domain. We're stepping into the S domain, the frequency domain, or we're working in the time domain. But if we remember that S and T are reciprocal quantities, then we can make the following. So this is now time, and this is frequency. If somebody says, well, what if I expand the time axis? Here, let's do a little mental exercise. If you have a sinusoidal waveform that's going up and down, up and down, up and down, and now I basically stretch that apart. I expand the time axis. What happens to how often that waveform intersects the horizontal axis? It becomes less frequent. So now if you expand the time axis, you are going to decrease the rate of change in the frequency domain. And just the opposite, if we now contract the time axis, we do what we were saying before. We now envision this slinky, and we have the slinky, the two ends of that, and we push it together. Now those up and downs, or the times that they cross the horizontal axis, is going to increase, and so now we would be thinking about increased or more high values of frequency. So now we're increasing the rate of change. Questions on those transforms, operational transforms? We have the time shift, the time delay, we have the frequency shift, and now we have a scaling of the time or frequency. And now, depending on what you are presented with for a function, you might be able to simplify your analysis or your computations by invoking some of these operational theorems or operational transforms. Let's do some ladder analysis. Now we're into the fire department, the ladder truck. Now here's the example, and maybe I'll try to explain where this is coming from. Let's say we have a voltage source, and we'll call it V. We have an inductor, we have a resistor, we have a resistor, we have another resistor, and we have a capacitor. And let's call this one C, this one L, and starting from the right side, I'll call that R1, R2, and R sub 3. What I want to do is I actually want to write some governing differential equation. Well, maybe I'm getting ahead of myself. What order of differential equation would you anticipate finding from this circuit? Second order, because you have two energy storage devices. And what variables would you like to concentrate on if you're writing governing differential equations? Eli and Ice tell us we want the inductor current and the capacitor voltage. So this capacitor voltage, let's say, is the output voltage, and that's the equation we want to find. Suppose we want a differential equation that's going to relate this output voltage V sub C to the input source V of t. And if we did some analysis, we might say, oh, well, we'll write node voltage analysis, or we'll do mesh analysis. In this case, what would you probably prefer to do if you were doing one of those two, node voltage or mesh? If you do mesh, how many mesh currents do you have? If you did node voltage, how many node voltages do you have? 2. Now what are you going to do? Node or mesh? Probably node. Now you have 2 equations and 2 unknowns instead of 3 equations and 3 unknowns. But you could do either one, and they should give you the same consistent result. And we will learn how to put this into the frequency domain and analyze with algebra techniques. But for now, let's see if we can derive the differential equation directly in the time domain using the ladder technique. And it's called the ladder technique because if you just use your imagination and put a ladder on its side, you have the rungs that go up and down. The R1 and the R3 and the C and the V are rungs of a ladder. And you don't really pay too much attention to what's happening on the sides, which are now on the ground and a little bit above the ground. But it sort of looks like a ladder, okay? Now, what we want to do is actually, instead of finding node voltage equations and then maybe doing some invert operations to get the expressions, how about we work our way from right to left? So we work our way from the output voltage all the way back to the source in a step-by-step fashion, and we can sort of check our thinking and our thought process along the way. And if we make a mistake, it's easy to find that mistake. If you just write node voltage equations, potentially it might be more difficult to find your mistake. Here's the ladder technique. And what I'm going to do is I'm going to just start interrelating a lot of these quantities. I can now relate that current, I sub C, with that voltage, V sub C. And I might want to know what this current is, so I'll call that I sub R1. I might like to know what this voltage drop is. I will call that V sub R sub 2. And I might also like to know what that current is. That's I sub R sub 2. Likewise, this voltage drop will be V sub R sub 3. This current will be I sub R sub 3. This current, hopefully, obviously, is labeled I sub L. And this voltage dropped across that inductor is V sub L. And now I want to really just find equations governing all of those currents and voltages and use that to work myself from the right to the left, or from the output to the source. And for now, we're doing it in the time domain, so that we will immediately come up with a second-order differential equation by the time that we're finished. How do I relate I sub C and V sub C? That's simply ice, isn't it? And we now know that I sub C, I'm going to be sloppy and not keep track of the time domain arguments. I sub C is C, V sub C prime, and prime is a derivative. There's ice, and that's I sub C. What is I sub R sub 1? In terms of, I want to end up writing everything in terms of V sub C, my R's, L's, and C's, and the voltage source V. You can rewrite I sub r sub 1 in terms of V sub c. It's the same voltage drop as what's across the capacitor, so that I sub r sub 1 is just V sub c over r sub 1. Now what am I going to do? Well, now I want to work my way back to the left. Let me look at that node. At that node, I can now rewrite I sub r sub 2 in terms of these two currents that I know in terms of V sub c and its derivative. Is that making sense? Using KCL at that circled node that I've circled in yellow highlight, I can now say that I sub r sub 2 is simply I sub r sub 1 plus I sub c, which is just c V sub c prime plus V sub c over r sub 1. So far, any variable that I've made my way across from right up to where I'm at, I've expressed in terms of that capacitor voltage or combinations of the capacitor voltage and its derivatives. Questions on that? I sort of interchanged the I sub c and the I sub r1, but hopefully you see that that's still okay. Now that I have I sub r sub 2, I can find the voltage drop across r sub 2. V sub r sub 2 is just r sub 2 times that current I just found, I sub r sub 2. So now I have V sub r sub 2 is simply r sub 2 I sub r sub 2, which now says that I have r sub 2 c Vc prime plus r sub 2 over r sub 1 V sub c. Again, that quantity, V sub r sub 2, is in terms of parameters and the output voltage or the capacitor voltage. Now that I have V sub r sub 2, what do I know? Now I know V sub r sub 3, because it's just V sub r sub 2 plus V sub c by KVL. Or this is now r sub 2 c V sub c prime plus r sub 2 over r sub 1 V sub c plus V sub c. I now know the voltage dropped across R3. I can compute the current through that resistor. That's simply I sub r sub 3, which is V sub r sub 3 divided by r sub 3. Or I now have r sub 2 c over r sub 3 V sub c prime plus r sub 2 over r sub 1 r sub 3 V sub c plus 1 over r sub 3 V sub c. Now what can I do? Now I can write I sub L. I know I sub L in terms of I sub r sub 3 and I sub r sub 2. Again, I'm working from right to left. I can now say that I sub L is equal to I sub r sub 3 plus I sub r sub 2. Or that's now this R2C over R3 V sub c prime plus R2 over R1 R3 V sub c plus 1 over R sub 3 V sub c plus I sub r sub 2, which is this c V sub c prime plus one over r sub 1 V sub c. And now I have quite a few derivative terms and some undifferentiated capacitor voltage terms V sub C. But that's now I sub L. Once I have I sub L, I can find V sub L, which is simply Eli, or L I sub L prime. And that now allows me to say, oh, let me collect all my common terms. I have an R sub 2C over R sub 3, this is times L, plus a C, V sub C double prime, plus an L times the other pieces, which is an R2 over R1, R3, plus a 1 over R3, plus a 1 over R1, V sub C. And that now needs to be differentiated. That's my inductor voltage. And I've almost worked my way all the way across the ladder. Now I can do KVL around the outer piece, and I have V is equal to V sub L plus V sub R2 plus V sub C. Does everybody see that? And those are logically understandable steps. And now you simply have to write down what those are, and you didn't have to do any matrix multiplications or inversions to try to find equations governing this differential system. We now know that V, the source, is V sub L plus V sub R sub 2 plus V sub C. Or V is now this L, R2C over R3 plus LC, V sub C double prime, plus L times 1 over R1 plus 1 over R3 plus LR2 over R1 R3 V sub C prime. Now I need to add in my V sub R sub 2, which hopefully is R sub 2 C V sub C prime plus R sub 2 over R sub 1 V sub C plus V sub C. And that's now a second order differential equation. It's linear time invariant because all the parameters, the R's, the L's, and the C's, we're assuming are constant. We now have a second order linear time invariant differential equation that governs the dynamic behavior of that circuit. And we derived it without doing too much really heavy algebra or manipulation. It just sort of fell out or just sort of appeared. And we understood each step in that progression. And now if we have a mistake, hopefully it's easier to trace back where that mistake might have arisen. Now, I'm getting tired of writing all the L's, the R's, and the C's, so let me just say that this is now V times some alpha 1 V sub C double prime plus an alpha 2 V sub C prime plus an alpha sub 3 V sub C. Is that okay? Now you can Laplace transform this. And if you needed to, you could keep track of all of those parameters, or R's, L's, and C's. I'm collapsing them all into alphas. If I now Laplace transformed that, I'll do the tough part. I'll Laplace transform the source, which is V of t. And that's just by definition some capital V of s. Somebody would have to tell you what is V of t in order for you to explicitly replace that with what it might be. And on the homework, they may say, oh, you have a DC source. If that's a DC source, then you'll want to replace that with maybe an amplitude, a magnitude of that DC divided by S. That's how you, because that's like a unit step, a DC source. If they do not specify what the source is, you have to leave it in this unspecified form, capital V of S. Does that make sense? If somebody said V of t was a sine wave of frequency omega, now you could replace that capital V of S with omega over S squared plus omega squared and obtain a more direct expression with less or fewer unknowns in the expression. What happens when I Laplace transform that second derivative? I'll do the hard part. It gets scaled by an alpha sub 1. But when you differentiate, what happens? What are you doing with the S? Now we're moving from the time domain into the frequency domain. And if we had two derivatives, if we had one derivative, what would that do in the frequency domain? Would it be 1 over S or multiplying by S? Now, derivative, we multiply by S, don't we? If we integrate, we're dividing by S. In this case, it would be S squared V sub C of S. But if we keep track of all of these initial conditions, we actually have some initial conditions to worry about. We have minus S V sub C of 0 minus V sub C prime of 0 minus. And all of those pieces get scaled by alpha sub 1. What is V sub C of 0 minus? This is your initial voltage on your output capacitor. And what does this one mean? V sub C prime of 0 minus. That's now the rate of change of that voltage at 0 minus. And you would have to be told that or determine what those initial conditions are. But those are time domain quantities that you now have to find a number for, and now you have minus S2 minus 10 or something, if those were your initial conditions. A voltage of 2 and a time rate of change of 10 at time 0. Plus alpha sub 2, now what do I have? I'm now Laplace transforming V sub C prime. And I probably should have been more explicit. That's now a time argument. We are going to end up with frequency arguments in our expression here. This is now S times V sub C of S minus V sub C of 0 minus. Plus alpha sub 3 V sub C of S. Questions on that? We've Laplace transformed a second-order differential equation. And we've incorporated all the initial conditions. If somebody says, oh, you have 0 initial conditions, then all of those time domain initial conditions are set to 0, and it cleans it up a little bit. You have no response due to initial conditions if they were all 0. We can now actually find or rewrite this expression really sort of into two pieces. We have an alpha 1 S squared plus an alpha 2 S plus an alpha sub 3. All of those scale or weight V sub C of S. And we actually give this a name. this is actually our characteristic polynomial. Because what are we trying to do? We're trying to probably find V sub c of t, the output voltage of the capacitor, in terms of whatever our source was. We now need to solve for capital V sub c of s, and then inverse Laplace transform, and we're done. So far, I haven't included any of the initial conditions, but if they are non-zero, I have to keep track of those. I have plus the pieces associated with the initial conditions. I have a couple of pieces due to the capacitor voltage at time 0, and then I have one piece due to its derivative at time 0 minus. Or I now have this, if I look at that, I have minus alpha 1 times s v sub c of 0. Oh no, this is now minus alpha 1. I'm looking at this piece right here. And I have another piece that is going to scale v sub c of 0 minus. I have a minus alpha 1s, and I have a minus alpha sub 2. If I now, is everybody comfortable with what I've done? I've simply tried to collect some common terms on the right-hand side. And what's scaling v sub c of s, I'm going to divide through by that, both sides, and then I will be able to solve for the Laplace transform of my capacitor voltage in terms of my source and the initial conditions, which I can then inverse Laplace transform. So I now have v sub c of s is equal to, let me clean this up. I'm going to just call this, can I call that, I don't remember now what the textbook calls it, characteristic polynomial. Let me call it d of s. So that I now have 1 over d of s, v of s, plus all of these other things, which are actually the initial conditions, divided by d of s. And I now have two pieces. I have this piece that's due to the forcing function. Part of my response is due to the forcing function, or the source. And the other part of my capacitor voltage response is due completely to initial conditions. Questions on that? Convolution time? Not quite. It's not quite warm enough to flip and slide just yet. Sorry, we'll get to convolution, and instead of slipping and sliding, we'll flip and slide, but that will make more sense as we get into convolution. But right now what we want to do is simply think about how do we go, now we're in the frequency domain. We want to get back into the time domain so that somebody can tell us, or you can tell somebody else, what is little v sub c of t. If they now tell you, oh, I was using a voltage source that was a decaying exponential, or my voltage source was an exponentially damped sine wave, or it was actually a cosine wave, or it was a combination of those three, you can now find out what your capacitor voltage is going to be as a function of time by taking this from the frequency domain back into the time domain. And we'll do that by inverse Laplace transforming. Meaning, if we want v sub c of t, we need to learn how to go back the other direction. How do we inverse Laplace transform? Questions on what's motivating? We need to be able to go from back and forth. We need to play in the time domain and maybe go into the frequency domain, or once we've played around in the frequency domain and found an expression for the quantity of interest, in this case it's the Laplace transform of our capacitor voltage, now we don't want to think about it in the frequency domain. We want to get it back into the time domain. We can now inverse Laplace transform. In a very general sense, here's what we want to do. Given some transformed quantity, in the previous example it was capital V sub c of s. In general it might just be some capital F of s. We now want to manipulate that expression, that F of s, into a representation which will allow us to associate these pieces in this manipulated form of capital F of s. We want to identify pieces that look like transform pairs in our table. So we want to manipulate capital F of s into a representation which can be associated with a Laplace transform pair. And if we can now pair that up, one column's the time domain expression, one column's the frequency domain. Oh, if we find it in the frequency domain column, we now can go immediately into the back into the time domain. Because we're dealing with one-sided Laplace transforms, that inverse operation is unique. We can go directly from the frequency domain back into the time domain. Finding that pair will allow us to write down this f of t, which is just the inverse Laplace transform of f of s. Suppose somebody gives you the following capital F of s. They give you 3s over s squared plus 4s plus 13, and they say, what is little f of t? And you go, oh. So now what is it? It's going to depend on how this denominator factors. We want to know what are the factors of that denominator. And then that's going to tell us quite a bit of information. In this case, if we factor that denominator, or does it have a special... Here I have an s squared plus 4s. That's begging me to see if I can complete the square. Yes or no? So if I look at this, I'm concentrating on the denominator. I can see that if I took s plus 2 and squared it, I would have an s squared plus a 4s plus a 4. meaning I can see that I have this piece lined up with that piece. And all I need to do is actually say, well, what do I need to add to this s plus 2 squared to give this side to make it look like the constant term is 13 instead of 4. And that's not too hard to do. If I simply inject, if I say plus 9, I can now say, oh, let me just add 9. And 9 is pretty nice. That's just 3 squared. Meaning, I now can rewrite f of s as 3s over s plus 2 squared plus 3 squared. Am I done? What do I know that denominator is, or how is that denominator jumping out at me? If I said, oh, plot the poles of that transform. Pardon? Now, if I tell you to plot, sorry, I was about to fall down. If I tell you to plot poles, what are you going to sketch? X's or O's? X's. There you go. Now we're getting there. Now we have X's. Where are those X's going to be located in the complex S-plane? On the imaginary axis, in the right half plane, and the left half plane. Left half, they're going to have negative parts, aren't they? They're going to be at minus 2. They're going to be on this vertical line that's 2 into the left half plane. It's 2 away from the imaginary axis, and they will be located off of the real axis a distance of 3. So we're now at minus 2 plus and minus j3. Those poles are immediately obvious from the way that denominator has been factored. Those are right at minus 2 plus and minus j3. Boom. What does that tell us? That tells us we have an exponentially damped sine and cosine. What's the frequency of those sines and cosines? That's the distance it is away from the real axis. That's the 3. That's our frequency, 3 radians per second. And how quickly is it damped? That's how far it is into the left half plane. In this case, it's only at minus 2. So it's e to the minus 2t cosine 3t or sine 3t. And what do those look like in terms of, so now I have this 3s over s plus 2 squared plus 3 squared. And you've just told me, I think, or I've begged you to tell me, that I might have a sine or a cosine piece. What's the cosine piece look like? It better have that s plus 2. That's this frequency shifting in it. And I don't know how many of those I have, so that's going to be an unknown k1. What are we doing? We're actually doing partial fraction expansion, but I haven't told you that. And what's going to go over in the numerator of the second piece? Well, that's my damped sine, so I have to make sure I enunciate clearly and put the p on the end of that damped. So that's a damped sine. Yes? And don't be calling it the other during an exam, okay? We need to be nice. What's it look like? What's the numerator look like of this damped sine? It's the omega over s plus a squared plus omega squared, and we don't know how many of those we have, so let's just say it's k sub 2. Now all we have to do is select K1 and K2 in such a way that we end up with 3s in the numerator. So K1 has to be 3, doesn't it? So now we're looking at the numerator. We're equating coefficients in the numerator. And we have 3s is equal to K1s plus 2K1 plus 3K sub 2. If I equate my coefficients of, well, let me do it the other way since it's quicker to fall out that way. If we look at the coefficients associated with the s piece, or s to the 1, I have one of those on the left, that's 3. And on the right, how many coefficients are, or what's the coefficient associated with the s term on the right-hand side? That's so easy, it's hard, right? So K1 is 3. If we now look at the constant coefficients, what do I have on the left? What coefficient scales s to the 0? Or what's my constant coefficient on the left? 0. I do not have one. But what do I have on the right? I have a 2K1 plus a 3K sub 2. But I already know what K1 is. I just found it. So I can replace that with 3. And now I know that 0 is equal to 2 times 3 plus 3K sub 2. Or K sub 2 is minus 2. If that's the case, now I know that f of s, I can rewrite it as 3s plus 2 over s plus 2 squared plus 3 squared minus 2 times 3 over s plus 2 squared plus 3 squared. And now what is f of t? Now I can write that down by inspection, because all I have is an exponentially damped cosine scaled by 3, and I have an exponentially damped sine scaled by minus 2. And I end up then with 3 e to the minus 2t cosine of 3t minus 2 e to the minus 2t sine of 3t. And what do I need to actually say? I need to say that these are all one-sided. That's valid for non-negative values of time. Or I could multiply the whole thing on the right-hand side by the unit step, u of t, where it would be acting like a switch. Now, can you sketch that quickly in your head, f of t? Or does it make your head hurt to think about that? You have a 3e to the minus 2t cosine of 3t, but you have sines and cosines of the same frequency, don't you? So you could now rewrite that as either a cosine or a sine. Meaning, if we look at this, we have the following. F of t we could rewrite as e to the minus 2t. That's common to everything. And then we have 3 cosine of 3t minus 2 sine of 3t. And what we want to do is we now want to combine these two pieces, the sine and cosine piece. They're of the same frequency, so we can actually combine those into one waveform with a shift. And then that's easier to think about. Now I just have a cosine or a sine that's exponentially damped. That cosine may be shifted in time a little bit, but that's easier to think about than having these two sines and cosines that I have to worry about, potentially. Questions on that? Do you know how to combine sines and cosines? If not, well, there's an app for that. There's an app for everything. I don't know if there's an app for that, but we will create an app for that at least at some point during the semester if it doesn't already exist. I'll see you then on Tuesday, but this should give you enough to work your homework problems for Tuesday. Oh, I didn't